Every volume we've looked at so far has had circular cross-sections. But of course, not all solids have circular cross-sections. What happens if we have something like the rectangular pyramid? Now, we can still use this idea of slicing, it's just that the cross-sections won't be circular. As long as, when I slice it, every single slice has a similar shape, we can still use this idea. So I've got a choice here. I could slice horizontally or parallel to the base. Each slice would become a rectangle. Now, if I was to slice it vertically, so parallel to, say, the height of the pyramid, then we'd get a different shape. Each slice would be a trapezium. I think if we do it horizontally, it'll make life a little bit easier. All right, so there's my slice. I'm going to give it some dimensions. I'll just call them X and Y. I mean, they can be any pronumerals you like. So I've just called them X and Y. But then the thickness will be in terms of a third variable, which I've called Z. So my slice, I'll just redraw it to the side here, is a rectangle. Its thickness is what I'm calling delta Z. Its height is Y. And its width is X. So my area function would be xy. However, I need it in terms of z. So I need to come up with a couple of formulas, one for x, one for y. So I'm going to break this problem down. Looking at it in 3 dimensions can be difficult. So I'm going to break it down into 2-dimensional problems. The only dimensions I'm interested in at this stage is x and z, because I want to find a formula of x in terms of z. So the dimensions I want to look at is the width versus the height. Now, if I was to look at that shape, what I'd see is a triangle. If all I'm looking at is the width, and the bottom there would be b, and the height, which is, of course, h. So how do I do this? Let's put our slice in. There's our slice. And we said the width of our slice is x, and the thickness is z. Well, the first way I could do this is using similar triangles. So let's just redraw the similar triangles. I've got one triangle there where the height is h, and the base would be half of b. And then I've got a smaller one at the top, which would be similar. And the height would be h minus whatever the z value is. Now I'm assuming z starts at the bottom. So 0 is at the bottom, and at the top it would be h. So the height of the second triangle would be h minus whatever the z value is. And the base would be half of the x. So there's similar triangles, so I know the ratio of the sides are the same. H over half b will be the same as h minus z over half x. Play around with that, and we get x is b outside of h minus z over h. And a lot of people like using similar shapes. Personally though, I prefer to use coordinate geometry. I'm trying to get a relationship between the x value and the z value. So my slice, I'm talking about 2 dimensions, the z and the x. So the first dimension, the z, we're talking about is the height of the slice from the base. That'll be my value for z. For x, it's the width of the actual slice. So when we're at the top of our triangle there, the z value, the height of the slice from the base, is h. The x value, the width of the slice, is 0. And then down at the bottom, the height of the slice is now 0 because we're at the bottom, but the width of the slice is b. So I've got these 2 coordinates, 0b and h0. And I can see from our picture that there's a linear relationship because it's just a straight line joining those 2. So we just do it like coordinate geometry. All right, let's find the slope. Now, in this case, x is where we'd normally see y, and z is where we'd normally see x. So our slope formula, which normally would be y2 minus y1 over x2 minus x1. But for this one, it's going to be x2 minus x1 over z2 minus z1. So b minus 0 over 0 minus h. And that'll equal minus b on h. So I have a slope. We put it into our point slope formula. Instead of y minus y1 is equal to the slope outside of x minus x1, now we're going to have x minus x1 is equal to the slope outside of z minus z1. So x minus 0 is equal to our slope minus b on h, z minus h. Playing around with that, we get the same formula. B outside of h minus z over h. Okay, now to find the y1, I really don't have to do all that working again because the only difference is that the base, instead of being b, is a. So if in my formula, everywhere I see b, I replace it with an a, and everywhere I see x, I replace it with the y. I now have a relationship for both the x and the y in terms of z. Let's put it into our formula. We said it was x times y. Expand out, and there we have a formula. Well, that's for area. So the element of volume will be that times delta z. It now becomes the same as we've been doing in the other cases. We want to sum all those slices. We're going from z was equal to 0 at the base of the shape, and we were building it up to z equals h. So we integrate. Now a is a constant, b is a constant, h squared on the bottom there is a constant. All I'm integrating is h minus z on z squared using our useful theorem. Add 1 to the power over the power, but don't forget to multiply by -1, the coefficient of z there. Substituting in, and there's our familiar formula for the volume of a period. And there's our familiar formula for the volume of a pyramid. 1/3 the area of the corresponding prism. Now normally you see length times breadth times height, but I've just got a times b times h because they were our dimensions. Another common one that we have is where we're actually placing slices on shapes already in the number plane. So in this case, we're saying a solid will have a circle for the base. Let's just draw that up. Now I've laid the number plane down flat. So we see our circle, radius of 2, x squared plus y squared is 4. Now each cross section is a square. So all the way along there's a square perpendicular to the base. Now I've made mine also perpendicular to the x-axis or parallel to the y-axis, whichever way you want to think about it. So the thickness of my slice will be delta x. So there's my first square. Then I can add another one, and another one, and another one, and so on, until we've got enough slices. There we go. It's an unusual shape. What we've basically got is a cylinder that's been shaved. I suppose it looks a little bit like a bike helmet, something like that. But the key thing is all we're interested in is the slice. So there it is. Now, our thickness, well, I was going along the x-axis for this one. So the thickness is delta x. The base, well, it's going to be twice the y value. It's symmetric about the x-axis. So we have a y value above and a y value below, 2y. And then, of course, the height, well, it's a square. So it's also going to be 2y. So my area is 4y squared. But I need that in terms of x. That's okay, because we know the equation of the base is x squared plus y squared is 4. So I can rewrite y squared as 4 minus x squared. And there's my area function. Okay, so my element of volume, 4 times 4 minus x squared times delta x, which means my volume, now we're slicing from -2 on the x-axis all the way to 2 on the x-axis. So we've got 4 outside of 4 minus x squared. I can use the fact that this shape's symmetric and go twice from 0 to 2. And so that's how I've ended up with 8 out the front, 4 times 2. And all I'm integrating is 4 minus x squared. Add 1 to the power over the power. Substitute in. And there's the volume for our unusual shape. All right. Let's have a look at an HSC one. We've got a solid which is being cut out of a quarter of a cylinder, and we're cutting in like a triangle. So we end with a bit of a wedge, some sort of rounded wedge. Now what have they told us? We know the length of BC is A, AB equals AC, A is the midpoint, and cross sections are rectangles. Well, again, it's the cross sections that we're interested in. So there it is, it's a rectangle. Let's give it some dimensions. The thickness, I'm going to call that, again, delta Z. Now I'm going to call the base, I'll call that X, and the height, I'll call that Y. A bit like our first one. So the area, again, is XY, but I need it in terms of Z. Let's turn our three-dimensional problem into a two-dimensional problem. So we're going to find Y in terms of Z. Now, if I look into the end of our quarter cylinder, all I would see would be a quarter of a circle, and its radius is, of course, R. The slice, well, all I'd see is the height of the slice. Okay. Then I know that's delta Z. I'm going to use the coordinate geometry idea. So I'm going to assume we're starting slicing over at A, and we're going to go across to X. I'm going to call my coordinates Z for the first dimension, Y for the second dimension. Now over at D, the Z value is going to be 0. That's where I'm starting my slicing. The height of the slice at that point is R. Now if I keep slicing to the right, eventually I'll get to X. And at X, I've travelled R units across from A to X. So that's my dimension for Z. The height of my slice is now 0. But you'll notice the relationship is not linear. It's actually a curve. The top of my slice, imagine you're at the top of the slice, it's travelling along that curve. Well, hang on. That curve is a circle. So I know the equation is, if you like, the equation of the semicircle that it's travelling on. Y is equal to the square root of R squared minus Z squared. Okay, so there's a formula for Y in terms of Z. Let's now find X. Now, to do this one, I'm looking straight down so I can see that base. So I'm looking at the base, ABC. Now, there's my slice, pop my slice in. I'm going to want coordinates. Z will represent how far we've gone from A, and in this case it's the line BC. However, I started it with the semicircle over here. Remember, I started at A. I've also got it started A here. I can't change the problem. So I know the Z value is still 0 at A. But X is representing the width of the slice. So at A, I've got the coordinates 0, 0. When I get to the end, then I've travelled R units along. The width of my slice is now A. I need to find a relationship between RA and 0, 0. Again, I can see it's a straight line. So, find the slope. A minus 0 over R minus 0. It's A over R. X minus 0 will equal slope Z minus 0. There it is. X equals AZ over R. We can now find our area. It was X times Y. Substitute in AZ on R times the square root of R squared minus Z squared. The element of the volume will be that times delta Z. I want to sum all those slices going from 0 to R. Now my integral, well, A is a constant, R is a constant, so I can bring A over R out the front. Z times the square root of R squared minus Z squared. Well, I can create the derivative out of front here, and we'll end up with derivative times function to the power of n. So there's my derivative, minus 2z to balance it out. I've also got minus and divided by 2 out the front. Derivative times function of functions to the power of a half. Add 1 to the power, 3 on 2, over the power, so times by 2/3. Substituting in 0 to r, and there we go. There is our volume. Now, that was a very tricky question. I think because of the curve in one of them, people assumed it was linear, but it's interesting to note that statewide, the average was 1.01 out of 4. And that gives you a bit of an idea of how difficult people found that particular question in the HSC. All right, so a few questions out of our Cambridge and a handful out of Patel as well. We'll have a go at those particular questions.